and I am delighted to introduce Matteo Capucci, who's going to be talking on From Categorical Systems Theory to Categorical Cybernetics. So please, Matteo.
All right. It's a great pleasure to be here. Thank you very much, Steve and Bryce, for organizing this and for inviting me, as well as many other wonderful speakers. So yeah, today I'm going to tell you about some ideas around general theory of what it means to look like a cybernetic system. And to me, cybernetic systems are, well, not to me, cybernetic systems are cybernetic systems with control mechanisms and interactive feedback, which usually, if you Google like cybernetic systems, you're going to see some diagrams like this, which go back a long way in the literature from the 50s, if not before. And so you see these are processes that somehow like interact with an environment. An environment usually has some kind of so you see here they call it disturbance, but it has some kind of dynamic, so it's doing something. And our goal is to sense what's happening in the system and produce some change, so act in some way on the system in order to restore some balance or achieve some goal. So systems like this are studied by control theory. It's probably the most successful branch of cybernetics so far. But also games. Games are cybernetic systems because players are trying to control a system, which is the rest of the game. Okay, so imagine yourself playing Monopoly or Risk and trying to achieve your goal. And learning theory, so neural networks and any kind of machine learning model is a control, is a cybernetic system. So it's try to solve a problem in which some feedback is given and they have to do something in order to make that feedback good. Okay, so and many other things. Okay, so there's already some ideas around how to approach this from these systems from the point of view of category theory. So probably the most popular and successful is categorical machine learning, which there's lots of work. And you're going to see like diagrams like this today, not many actually, but this is how we represent such a cybernetic systems. In particular, this is machine learning model trained by gradient descent. So there's a system which is being controlled, and over it there is a control, okay, which in this case is doing some version of gradient descent, and around it there's an environment, which is in this case is some like apparatus furnishing an initial state, so like some input, and then evaluating the output of the model based on some loss function, okay. And also games that look a lot like this, which have probably a longer history, but they've been pinned down quite well only recently, and they look the same. Now, this part of the system represents like the game we're playing, and this part is the dynamics of players that are trying to achieve something in their game. Okay. But what does it even mean to study cybernetic systems? So what is, in a sense, what does it mean to approach this? So there's two parts. One is to understand the ontology of cybernetic systems, which is a fancy way to say understand what it even means to be a cybernetic system. Okay, so what is made of, and what are the kind of interactions that a cybernetic system can take part in. What are its interfaces? What is its like anatomy, and how do we write down the model of cybernetic system? And on the other hand, there's the phenomenology. So what does a cybernetic system do? Okay, so what can we observe about its dynamics and its evolution? And in particular, how like the first set of questions relate to this second set of questions. So if we have a cybernetic system which is made of multiple parts, how do we relate observation that we made of these parts to make to build a picture of the whole? And can we ask questions such as like, are two cybernetic systems the same from the point of view of what they do? So this is the kind of idea that so these are the kind of questions we want to answer with the theory of cybernetic systems. And there's actually like a good framework to do so already, which is categorical system theory, which is answering these questions for open dynamical systems. So instead of being systems that can be controlled, they're just systems. Okay, we don't talk about any kind of control. And this framework has been built by David J. Myers, and who wrote a book you can find later in the references. It's a very long book with tons of really nice ideas and examples in mathematics. And he's gathered like many ideas from the literature and added some extra. So in the literature, we already have a bunch of categorical system theory happening. So very long, like, how do you say, a very rich line of research has been on algebras for operas of state diagrams. So we represent systems with some kind of notation, and this notation forms an operad, and actual models of this like syntax that we use to describe the models are given by algebras for such operas. Okay, so for example, wiring diagrams, string diagrams, bubble diagrams, these are all kind of diagrams that we use to specify systems. Algebras of this are going to be some kind of systems. And this is things that you can describe in categorical system theory. There's also a slightly older line of research that's been recently reanimated by some people in Tallinn, which is about transition systems and open transition systems, which are like you build categories, by categories of this using some kind of the looping suspension construction. And this can also be captured with categorical system theory. We're going to see this. And then there's double category structure co-span, which are really close to what categorical system theory is doing, which are ways to talk about systems that are made of circuits and connect in the way that you connect circuits, like plug-in ports or wiring together like devices, and finally there's a very wide notion of what process theory means, which is given by symmetric monoidal categories, and this is very popular in has been popularized by people doing categorical quantum mechanics, and we're going to see a bit of this today as well. So what is in common among all these approaches to studying specific kind of systems? Well, a very fundamental idea is that processes, so things that do things, are composing morphisms of a category. Okay, so that's why I'm here, and that's why people have been using category theory for a long time to study systems. Okay, because processes can be plugged one after the other, and this kind of plugging is exactly the kind of plugging you can do with morphisms in a category. But there's more. So this is telling us how to specify and describe processes, but when it comes to their behaviors, so when it comes to the phenomenology, to refer back to that slide, then there's actually a common theme, which is to study lax functors or functors of some kind from a category of processes to usually something that looks like relations or bimodules or spans or matrices of some kind. Okay, so for example, this is the paper by Categories of Processes, where they describe this this functor that takes a circuit and associates to it a span describing its equilibrium. Or this is Baez and Master in their paper about open Petri nets. They describe this black boxing functor that takes a Petri net and maps it to a relation that describes its reachability problem. And this is an even older paper by Spivak, in which he proves that steady states for a very general notion of dynamical system compose like matrices. So a system can be mapped to a matrix of steady states, and the steady states are indeed matrices in the sense that the composition of systems maps to composition of matrices. Okay. So in categorical system theory, we take this and we add two important things. So first is that, and that's why I'm here in particular, processes are organized in double categories. Okay. So we interpret a double category as to be talking about processes, which are given by the vertical maps, and maps thereof. Okay, so we add this other dimension that describes not just how what processes are and how they compose, but we describe also how processes map to one another. Okay, and also this, like as a byproduct, explains why behaviors even land in things that look like spans or matrices or things like that, because when you take the home functor of a double category, well, the horizontal home functor, it naturally wants to land in spans, and we're going to see that many behaviors are given by this kind of home functor. So that's why it makes sense to map behaviors, to map processes to behaviors in span. And secondly, and I think this is maybe the most important, this like addition to what's read in the literature, is introducing a distinction between processes and systems. Okay, so this is a bit subtle as a thing, but the point is that a process is something that does something, but has no like internal state, has no, in a sense, there's no individuality. It's just like medium that we use to actually plug systems together. Okay, so we end up describing systems as a thing that is acted upon by a category, or better, a double category of processes. Okay, so we're going to see that system theory is given by this kind of actions. And yeah, here I wanted to make the point that like systems and processes are different. So for example, a dynamical system in a classical sense, it's an endomorphism on some space of states, and we can equate it in observable to look what's happening in the system. And this is a system, but what is a process that connects systems together is a map between observations. Okay, so these are very, very different things, but you see that things, if you can remap observations, that you can map between systems. Can you hear the noise? Is it loud? Okay. So yeah, there is a distinction. It's not very well known in, I think that's a genuine innovation of categorical system theory. But let's see what are we actually going to talk about today. So first, I'm going to tell you about categorical system theory. So just to clarify this even more, this is not something I've done. This is David Jesmeyer's work, but I've been studying it very diligently and building on it. And I want as many people as possible to know about it because it's really a great idea. So I'm going to tell you about it today. We're going to see theories of processes with examples. You're going to see what theory of systems is with some examples. And I'm going to tell you about this idea of functorial behaviors. Okay, so determining behaviors functorially. And this is going to happen in double dimension. Okay, so this is all about double categories. And then later I'm going to introduce what I came up with, which is an extension of this framework to deal with the kind of systems that I was telling you about at the beginning. Okay, so systems in which there is a separate system which is doing some control. And for that part of the talk, we're going to climb up one dimension and go into triple dimension. Okay. So just some notation setting. So to me, double categories are weak by default, and functors are lax by default. I'm following Grandes and Paredes conventions mostly when it comes to notation. And then, of course, vertical arrows are going to be denoted by this or by other kind of marked arrows. And these are vertically, these are the loose ones, so the one composing weakly, and horizontally we have the other kind of arrows. And then when you see this fancy set here, so blackboard set, this is to me the double category of spans of set, whereas blackboard cat is the double category of categories, functors, and profunctors. Okay, so I'm going to use this notation. which is a bit different from what you find in the book by David. And I'm also diverging on some terminology. So you might go to the book later if you're interested and see some differences. Don't be afraid. It's the same thing. Okay. So categorical system theory. Ambulance. So as I anticipated, the idea of categorical system theory, or at least my conceptualization of it, is that we start by, like, if you want to study some notional systems, we start by thinking about what are the processes that these systems interact with, okay? And we build a double category which organizes these processes and maps of processes. And then from this, we're going to give a double index category of systems, which is those like given by categories indexed by processes. I'm going to tell you more precisely about this. And then we describe behavior as some like notion of mapping from the system theory we specified, which is this kind of functor, into like canonical system theory, which is the observational theory, which is basically built from spans of sets. Okay. So what is a process theory? Well, a process theory is a double category, full stop. Okay. What changes is the way we interpret this, the components, like the data of this double category. So it's an attitude on the concept of on the mathematical definition of a double category. So instead of saying objects, when I'm studying a process theory, I say boundary or interface. Okay, so imagine these little dots that didn't even bother naming as like places that mediate some interaction. Okay, something is gonna be exchanged there. Vertical morphisms are going to be called processes. So these are maps that have a dynamics, do something, okay? Whereas horizontal morphisms are maps between the interfaces. So they just tell me how one interface can be mapped to another. But these are, you should think of this as like kind of external. They do not model something that happens in the systems I'm studying, but they model something that me as a modeler uses to compare different interfaces. Okay, so there is no dynamics happening here. And finally, squares are maps between processes. Okay, so they're mapped between processes, which are, so the processes are of course these two sides, and the map fills the square, but we mediate this mapping by two maps between the interfaces of these processes. So to go on about describing a map between processes, we first specify ways to compare their interfaces, their boundaries, and then we give a way to compare their dynamics. Okay, this is how we interpret the data of a double category. So in principle, any double category could be a process theory. In practice, you should give me a good reason for why I should think about that specific double category as a process theory, right? So let me also add something that, so many people think the process theory is really, so well, process theory is already a term in literature, actually, I should say, and it means symmetric monoidal category with attitude again. But I want to make a more nuanced description, so I call a double category with a monoidal structure on it a concurrent process theory, okay? Because I think there's many other structures that you can equip a process theory with. This is just like the bare minimum, and I want the bare minimum to be called a process theory. And then on top of it, you can add all the nice structures that you want. And for example, if you're interested in processes that happen at the same time, then you're gonna want to use a concurrent process theory. And this is probably 99% of the cases, to be fair, but that's all we're going to see today. Doesn't need a monoidal structure, right? It's just like it's a bit more fundamental, you could say. So let's see an example. So this is a very dear example to me. This is the process theory of lenses, okay? And it's defined in the following way. So boundaries, so objects of this double category I'm defining, are pairs of sets. So we have every boundary is made of two things. And why two things? Because processes are given by lenses, which are at the end of the day, a notion of bidirectional transformation. So in this boundary, we have the lower part, which mediates an interaction going forwards, whereas the upper part mediates an interaction going backwards. Okay, so a process between two pairs of sets, so two boundaries, is given by a map between their lower parts, and you see a map between the upper parts, with the caveat that we remember something from the previous interaction. So we imagine P sharp to happen after P. Okay, it's a kind of like question answer thing. Okay, and since P sharp happens after P, it remembers something from what has happened before. Okay, so there is a notion of like this process kind of has some memory about its past. And how do we compare instead boundaries? We use charts. Charts are very much like lenses in the sense they are bidirectional, but they're very much not like lenses in the sense that both maps go in the same direction. Okay, so on the bottom part, they look exactly the same, but the backwards part, which lives on top, is actually not backwards anymore. Okay, so we map A plus to C plus, and we map A minus to C minus, but again, we remember what happened before. Okay, so there is no like dialectic anymore. There's no kind of like question answering. It's just like, oh, here's my boundary here. Now I'm going to map it to a new boundary in this way. Okay. And squares, so maps of processes, turn out to be just commutative squares. So there's actually no data inside these squares. So we're defining a thin double category, which is a double category in which if you can write down a square, then you can do it in most one way. Okay. And well, this looks very messy, but what it means is that it's basically a commutativity condition. We want to say that if we do this process and then we map its result, it's the same thing as mapping the inputs and then doing the other process. Okay, but this is bidirectional, so you have to be a bit like careful in the way you formulate this commutativity. All right, so another very important process theory is the observational theory. So if you give me a category C with pullbacks, we know we can build a double category of spans. And the way we think about this double category now, so we think of it with the aptitude of a process theory. And so the vertical morphisms, which are the processes in this process theory, we interpret them as processes of which we forgot everything except their observable behavior. Okay, so we don't know how A gets mapped to B, but we know that if you give me a measurement on the boundary A, if you give you when I say measurement, I mean observation, it's the same thing. If you give me an observation on A and observation on B, there's going to be a set of states that are compatible with those observations I'm making. Okay, well, I said set because we usually care about the case in which C is the category sets, but you can define this in more generality. Okay, so this is just the double category of spans. Now, what's going on between systems and processes? As I said, systems are kind of like processes, but they might have a very different aspect and very different form. And in particular, we think of them as somehow self-contained and stateful. Okay. So an example we're going to see is Moore machine. So a Moore machine is like a lens because you have like a map that gives me an output, and given an input, I can update my state. But you see, it's not really just a lens. There's like more to it. In particular, I think of this left side as being like a state. Okay, one object instead of being two interfaces. Okay. In the same way, you can consider among all spans things that like one-sided ones. So we forget about one leg, we don't have it. And this is like a system in the sense that it has a set of states. Remember, in the observational theory, which is what the spans give you, we forgot everything about the dynamics. So we just know there is a state, and we know that we can see some things about that state. Okay. So a system observationally looks like this, a map from S states to all observables. Okay. So a system theory is given by a functor like this. which is not really a functor in the sense that it's better conceived as an action of P on a category, okay? But of course, this is given by the same data of a functor, provided we can give meaning to this transposition thing, okay? What it really means is that, yeah, we're gonna map objects to categories, so interfaces to categories, processes to functors, and maps of processes to profunctors and maps of profunctors, okay? And yeah, again, one can enrich this definition with more structure. So for example, we care about monoidal structure, we'd like to ask this to be a lax monoidal, okay? So have some notion of tensoring between systems that is compatible with the tensor on processes. But let me explain to you better what this structure means. So let's unpack this definition. So this functor is going to give for any boundary A in P a category, sys of A, which we think of a category whose objects are systems with boundary A, and maps are simulations. Morphisms in this categories are ways to compare a system to another. Now, if you give me a process between A and B, then I can extend whatever system I have on A along that process and get a new system, okay? So this functor here describes how we can given a system on A, P acts on it by like attaching to its interface and pulling it back, like basically defining a new system which now has interface B, which is the other interface of the process. Instead, if you give me a map of boundaries, then I get a profunctor. How do I think about this profunctor? So this profunctor is going from systems over A and systems over C, okay? Now, H is giving me a way to map A into C. Okay, so now if you give me a system on A and a system on C, S and R, then the set associated to them by the profunctor sys H can be thought of as the set of possible maps between these two systems, which are mediated on their interface by the map H I've given. Okay, so you can imagine S and R as mapping into each other, but since they live on different interfaces, you have to tell me how their interfaces map into each other. Okay, you're going to see examples. And then finally, if you have a map of processes, which is a square in P, my process theory, then I get a square in categories, in the prior equivalent of categories and profunctors, which is extends a given simulation of system along a simulation of the processes I'm attaching. Okay, so I have a simulation of a system over A, I have into a system over C, and now you extended both, one with P and one with Q, but you have a way to map P into Q. So now if you give me a way to map the system that lives over A to a system that lives over C, then you can extend it along the new way you have, along the way you have to map the new pieces you attach to both, okay? It's a bit contrived, I know, but it works really well. So let's see some examples. So let's start from something very simple. So as I said, a dynamical system, in like traditionally speaking, is just an endomorphism in some category of spaces. So give me a space S, and there is a dynamical map that maps a state to a new state, okay? But of course, like I want at least to observe this, because otherwise it's just like a closed system, there's nothing I can do with it. So usually it's good to like consider some kind of observable over it, okay? So this is a notional system. So we might think if this can be captured by the framework. Okay, so what is the notional processes between the systems? Well, I told you already, because I told you that a map between the systems before, I said it's a map that extends the observation. Okay, so the dynamics doesn't interact with anything except through the observation that I see. So if I have a way to like map my observations to new observations, for example, I have a process, some kind of like measurement device that processes my observation and produces some new data from it, then this is just a map that can extend the observation. And then without like a more accurate model what's going on, then also maps between observations, so between boundaries, are going to be basically maps in S as well. So here is one of those cases in which the double category is kind of not very expressive unless we like really commit to some like specific notion of dynamical system, in which case we can introduce some distinctions between this that we might care about. For example, this map might be effectful or have different intentional properties than this. But anyway, for sake of simplicity, now let's just look at the double category of squares in S. Okay, so S arrow. Now this is indexing dynamical systems, because like if you give me an interface O, I can give you the category of all pairs, well, all triples of a state, an update map, and an observation that lands in O. Okay, and a map in that category is going to be a map G between the states that makes this commute. Okay, and now if I have a process which is just a map from O to a new interface, then of course I can just like compose my observation map, as I said, with that and get a new dynamical system with the same state space, the same update map, but a different observation map. If you give me a map of boundaries, which is again a map in S, I get a profunctor, which like think of the interpretation. This should be giving me a way to, if you give me a system over O and a system over R, sorry, system over O prime, then you should give me all the possible maps from the system S over O to the system R over O prime that are mediated by this map of boundaries. So these are going to be all the map between S and R, the state spaces that make this diagram commute. And you see that here at the bottom, we have H. And finally, if you have a square, then we can just extend, like if you have something like this, we can just attach the square we have on the bottom. And then given a map between the systems, we get a map between the systems, okay? Now let's see another example. Moore machines are a better version of dynamical systems, okay? So now instead of just having an observation, we also can get some input. So instead of just being open towards the outside, we also open from the outside. I don't know if you can say this, but I can get something from the outside. So Moore machine is a state space S together with these two maps, okay, which are a lot like the ones we had before, but now there's an extra input in the update map, okay? So the update, the transition from a state to a new one, depends on some input that arrives from the external world. Okay, so I think like one of the most common things is to have I being like time, and so you have like a transition that changes depending on time. Okay, it's called a non-autonomous system, but it can be anything. So usually these are some kind of finite state machines. So I read some character and I do a transition in my automaton, and then I spit out like if I am accepting this string yet or not. But anyway, this gathering a category. So if you give me two sets IO, then I can give you a category whose objects are Moore machines. So these pairs of arrows, and whose maps are given by basically charts that make the square in lenses commute. Okay, so it's G is going to be again a way to map S's to R's that commutes with the dynamics. Okay, but now this can be seen like this commutativity condition can be given in the same way that the commutativity condition was given for squares of lenses, like in the double category of lenses. And in fact, Moore is a system theory over lenses. Okay, so it's a notion of systems we can give for lenses. And indeed, like if I have a lens, sorry, this should be backwards, but if I have a lens, then I can compose it. And if I have a system over like IO, then I can compose it with that and get a Moore machine over IO, I prime O prime. If I have a profunctor, I can do the same maneuvers we did before for dynamical systems and get like the set of mappings that are over the chart that I give and get a profunctor out of that. And then if I have a square again, I can say, if I have a way to compare systems on IO and to systems to J over JQ, then I get a map to compare system over I prime O prime and system over J prime Q prime, which are being given by extending these systems here with the processes P and Q. Okay. Which again, we get by basically stacking squares. And finally, I want to tell you about the observational theory, which is very important. So the observational theory is a theory over spans. As I told you before, like we can think of an observational system as being just a space of states with an observation. So if and this is going to be a system theory over the observational process theories, hence span C. Okay, so over a given object in span C, we get a category whose objects are maps into I in this case, and maps are commutative triangles basically, and we can reindex along a span, and we can get a profunder from a map in a very similar way as before, and we also get squares from squares of spans. Okay. So we get a system theory, and in particular, when C is set, we get a very important system theory that is just called ops. Okay, which is a very sort of like a universal system theory in the sense that I can always get a map from, I can always get maps to it. And let's see what I mean by this. So if you have two system theories, so this kind of funters from a double category into cat, double index categories, then a morphism is basically a commutative triangle here, which is filled by a vertical lax natural transformation. So a very scary thing. What it means is that for every object here, we get a funder between systems over J and system prime over phi of J. Okay, and this is only lax natural. Okay, and this has a meaning I'm going to tell you about in a few moments. Now, categorical system theory can be formulated as the study of system theories, which are this kind of maps, so double index functors, through maps into between like whatever system theory you're interested in into the observation system theory. Okay, and these maps I call behaviors. Okay, so behavior is a map, so it's mostly like a notional behavior, you could say. So for every system, it tells me a way to map that system to a map of an observation. Okay, so a map from its set of states to a set of observations. Okay, and depending on my notional behavior, this map is going to be different. Okay, what is that I can observe about the system? B is an answer to that question. Okay, and you can always build behaviors by basically building a co-representable map. What do I mean by this? So if you have a system theory and you choose a system, so an object in one of the fibers of this indexed double index category, then you can build this map, which so the part between the indexing categories from P to set is given by a horizontal home funder out of I, which is the interface of the system we've chosen. Whereas between the fibers, we define it like this. If you give me J in P, then I want a profunder from a funder from systems over J to families of sets indexed by maps from I into J. But this is the same thing as a funder that given a system over J and a map of interfaces into J gives me a set, but I can use the action of H as a profunder to get such a set. Okay, so what this means is that this is assigning to a given set the family of all possible simulations of the system S that I've chosen in the system T that I choose here. Okay, so we look at all the ways. So we fix a system S and we look at the possible simulation of that system in every other system. Okay, so we use system S as a kind of archetypal system for whose dynamics we're interested in recognizing in other systems, and that's going to be our notional behaviors. Like, does this other system, in how many ways can a given other system behave like S? So the system that I elected as the most important system. Okay, but this is a bit vague. Let's see an example. So a very important notional behavior is like fixed point or equilibrium behavior. Okay, and this is given by what is a fixed point behavior is a system. The fixed point of the equilibrium of a system happens when the system is doing things, but it really like stays in the same state or doesn't move much. Okay, it's in a kind of like standstill. So in many cases, so here I'm given this for more, but it also is true for many other theories of systems. There is a system which is sort of like trivial. In this case, it's like the Moore machine that does nothing. Okay, has no state. Well, has one state, no input and output except the trivial ones, and the dynamic is nil. And if we map this state, this system to any other system, what we're trying to say is, can I find a way to recognize this dynamics into a system you're given? So if you give me another Moore machine and you ask me, what are the ways in which this Moore machine T can behave like fixed? Then this means that I'm going to look at all the possible maps from the fixed point Moore machine to the Moore machine you've given me, and when I can find one, then I found a fixed point. Then I found a fixed point of the Moore machine T. Okay, because I found a way in which the Moore machine T can behave as if it's not doing anything. And if you unpack indeed the definition of, so this is the functor I defined previously, instantiated in this case, and you unpack the definition I've given, then you get that this functor is going to map fix to the set of states that given a given chart. So given like input output I give to this machine, well, these states are always going to repeat. Sorry, and I'll see there's a bunch of typos. So these S's are supposed to be T's, of course. Okay. So if our notion of behavior is fixed points, I'm interested in studying equilibria of systems, it's very often the case that we can do so by defining this morphism and studying, this behavior, so this morphism of system theories and studying that. Okay. So in particular, there's a very nice theorem in David's book, which proves that despite the fact that this map is supposed to be only lax natural, then for like this system theory and this particular system, then this map is actually going to be strongly natural, or like natural full stop. So it's not actually lax, which is a good thing for reasons that I don't have the time to tell you, unfortunately. So let's recap this quickly. So we're seeing the categorical system theory studies double categories of processes that are indexing systems with like these double index categories, which are actions of P on categories of systems, and study behavior as maps of a given system theory into a very special system theory, which is the system theory of observations. Okay, so the system theory that only cares about what we can see about a system and not what we can, and not about the dynamics. Okay, and moreover, there is a recipe that always gives us some notion of behavior, which is taking the co-representable ones. Okay, so the ones you can get by looking how a chosen system here can be mapped in every other system. Okay. And these are very expressive. Okay, many of the examples that are in the literature as shown before are just like co-representable behavior, so we don't even have to define all the 100 coherence things that we need to define a vertical lax-nitride transformation. So this was a very quick tour of categorical system theory. In the few minutes that are remaining, I'd like to tell you about some ideas I have regarding its extension to cybernetic systems. Okay. So in categorical cybernetics, again, we study things like games and learners. I mostly care about games, and these look like this within this. So it's kind of established by now that cybernetic systems can be distinguished as those systems that have the structure of a controller. So here in blue, sitting over a green thing, okay, which is a controllable or a controlled process, okay. And moreover, these are very well modeled by categories, okay. Why is it so? Because I can think of morphisms in a bicategory as controllable processes, so processes that need someone moving the levers to function. And I can think of a morphism between these morphisms, so a two-cell, as some kind of control process that tells me how the problem of controlling G can be reduced to the problem of controlling F, okay? So, and in particular, the way that these things compose is the way that controllable processes compose. So if you have, so you can stack control processes. So if you have two consecutive controls and you compose them, then you can reduce the bottom controllability problem to the top controllability problem. And if you stack from side to side, you stack two of the cells side to side, then you can compose two controllable processes as you would compose any kind of process. And then the structure of the bicategory gives you a way to make sure that the two control processes you have on top are still on top and give you a well-defined control of the composite, okay? And after me, David Jesmeyer is gonna talk about a very specific construction for this bicategories, which is already specialized for the kind of attitude I was talking about in this talk. So you're gonna see a bit more of this later. Now, let me skip this. So it's a good idea, therefore, okay, let me not skip this. So you can arrange processes that are controllable and processes that are not controllable into double categories, which have the properties of, is this, no, which have the property of having all companions. So the idea here is that you have now a double category whose vertical maps are simple processes, horizontal maps are controllable processes, and you can always turn a simple process up to become a controllable process, which is actually trivially controllable, okay? And interpret the two-cell here to be a control process, okay? So we kind of unwrapped the globular cells we had here, sorry, these globular cells, we opened them and we added this extra thing. And again, I think the talk of David will clarify why this is actually a good idea. But now let me conclude by telling you what is a notion of a cybernetic process theory. So here we have a double category, but this is not a process theory because all the maps involved in the double category are processes. So if you recall, a process theory was a double category in which the vertical maps are dynamical, so they are processes, but the horizontal maps are not. They are maps between processes. Whereas here, we have controllable processes, simple processes, controlled processes. They're all processes, okay? So if you want to add a notion of mapping between this, and then allow me to compare controllable processes and controllable processes and control processes and control processes, then I need to add another dimension. And this is why we're going to go in the triple dimension. So a cybernetic process theory is a triple category, which is, I'm going to define a triple category basically, okay? Again, it's a triple category with attitude. So it's really just a triple category with an interpretation that we give it, okay? So if you don't know what a triple category is, just follow this definition. So in a triple category, we have three different notions of one cells. Okay, sorry, there should be a one. So first of all, the objects are again interfaces, and we still have simple processes as the vertical maps. This maps in the transversal direction, so it's kind of oblique, are maps between interfaces. So again, static and non-dynamical ways to compare interfaces. And the horizontal processes are, sorry, the horizontal cells, one cells, are processes that we can control instead. Okay, controllable processes. Okay, so we have now two kinds of dynamical maps, and this correspond to the two directions in which this categorical structure is weak. Okay, so these are going to compose weakly, these are going to compose weakly, and the weakness in this composition is going to be witnessed by maps in this direction. So the transversal direction is like the horizontal direction for double categories. Okay, it's a strict direction. Now, at the two-dimensional level, we have this blue notions of two cells. So we have, again, we have three kind of two cells. So there's a kind of two cell we're already familiar with, which is this one. These are called vertical two cells, okay? So their boundaries are given by processes and maps. And the vertical two cells map processes to processes in the same way they did in a process theory. So this vertical part here, these vertical two cells form a process theory of the kind I told you before. Now, these two are new. So first of all, these ones are called horizontal two cells, and they give me a way to map a control process into another controllable process. And again, this is given by a map here, which is mediated by maps between their interfaces. Whereas in these cells here, which are called frontal or basal two cells, are control processes. Okay, so these are dynamical in a sense. Okay, they're not maps of processes, but they are processes. Okay, and these are the ones I just introduced now when I told you the definition of a cybernetic company. So this map control processes to controllable processes, but they are like control processes, and they have like other two processes on the side, basically for formal reasons. And finally, and this is what I'm going to conclude on, we can see a cube. So if we assemble enough of these two cells together, we can close them into a cube, and this is the highest dimension in a triple category. And you see the sides of this cube are given by a control process in the back and a control process in the front. And then all around, you have maps between the boundaries of these control processes, okay? So you have maps of controllable processes on the bottom and on the top, maps of processes on the side. And so a cube is defined in the middle by a map of controls. So a cube is going to witness a map between the system on the back and the control system on the back and the control system on the front. Shall I wrap up like now?
In the next 2 minutes would be
okay.
Ideally.
So I'm just gonna show you so an example of what I mean. It's not gonna tell much, unfortunately, but this is reproducing the idea we've seen before of fixed points being given by mapping a trivial system into a system we're interested in. So we can build a cybernetics process theory where we can talk about games, for example, and one can show that if we have a game which is given by something like this, but now represented as a frontal cell, so a controllable process with a control on top, and we map the trivial controlled fixed point. So this is, again, something that does exactly nothing, but it does nothing in many dimensions now. Now, if we map this in a suitable way in this game, then one can prove that we're going to get exactly the equilibrium of this game, so the Nash equilibrium. And okay, I'm gonna skip this. So I wanted to tell today about not just what categorical system theory was, but also categorical cybernetics. And this is all work in progress, actually. So there is a notion of categorical or cybernetic system theory that is kind of 80% there. And from there, there's lots of work to do. And for example, starting from categorical system theory, I think there's a lot of things to do there, starting from examples that can be found pretty much everywhere you look. And I think it would be interesting to write down more of this stuff and to understand in which way this categorical structure can be exploited to say things about this. In particular, the use of co-representable behaviors gives you not just behaviors, but like a compositional structure for them. And it'd be interesting to look at what you can say about machines in this way. And then like in cybernetic systems theory, there's basically everything to do, starting from finishing the theory to actually like understanding and writing down examples. I have some applications to game theory that are there, but there's surely applications you can find in control theory and machine learning. And I'm very interested in understanding what this can, if we can say something interesting about behaviors of these systems again. So that's basically the morale of the talk. Can we use this nice structure to find a good way to talk about behavior? And there's a lot to say about behaviors of this thing, starting from equilibrium concepts in games and ending in things like the free energy principle, which has been very popular lately. Sorry about being over time. Thank you very much for your attention. And please, if you have any questions, go ahead.
Okay, thank you very much. Let's start by thanking Matteo for the lovely talk. If anybody has any questions, we've got time for a few questions. If anybody would like to unmute, raise your hand, or post in the chat and I can read them out.
Hi there, can you hear me?
Yes.
Yeah.
Hey,
I don't know who's talking, but I can hear you.
It's Martin Schild. Quick question. Your triple categories that you mentioned before, do they have 3 different kinds of arrows?
Yeah, so a triple category is a thing made of cubes in the same way that a double category is a thing made of squares. So you have 3 arrows, like 3 different notions of one cells in 3 different directions, 3 different notions of 2 cells, and 1 notion of 3 cell.
Okay, cool. Thanks for the answer. And do you think are the 3 types of arrows really not comparable between one another, or can you see all of them as being just 1 or 2 classes?
Right. So in many examples, so something I was a bit quick here, but so if you manage to follow, this notion of 2 cell is actually required to be a company. So I want, in some sense, I want processes to be special cases of control processes. So in a sense, you can simplify the structure by forgetting about this direction and be like, in this direction, we just want to have identities. And all the dynamical information that it's in the 1 cell, we can encode in just the control processes, okay? So you can simplify it in this way in general. And then in any given example, of course, there's going to be some things you can say, I think. So yeah, I think a good thing about this framework is that it's actually quite easy to decompose in many parts. It might look a bit scary because it's triple categories, so much data, so many things, but you can always kind of ignore the things you don't want to use if you're careful enough and work at least 2-dimensionally or even in lower dimensions. So you can just look at the things you were really interested in.
Okay, cool. Thank you so much.
Okay, we have time for one more small question, if anybody has a tiny question.
I have a tiny question.
Please.
Thanks for the talk. This is very enjoyable. So you've been calling certain double categories companies. I was wondering what you meant by that.
Can you repeat, David? Sorry.
Sorry, is my audio all right?
Yeah, it's a bit low.
You were calling certain double categories companies, and I was wondering what you meant by that.
So you were wondering, I didn't get the last part.
Sorry, you were calling certain double categories companies, and I was wondering what you meant by that.
Oh, okay, sorry. A company to me is, well, I think you told me this name. A company is a double category with all companions, which means you can basically, you find these universal cells for any given vertical cell here. That allow me to say that you can always think of a vertical cell as a horizontal cell. So sorry, here I should really say you can always think of a tight cell as a loose cell, because here I transposed everything. So these are really like tight ones. Okay, and the idea is, in the case of cybernetic components, the idea is you can always find a simple process or process that doesn't need any control. You can find it as a controllable one, okay, and which is trivially controllable. Okay, so you have this option of thinking of this as a controllable process.
Thanks.
Okay, thanks. Let's thank Matteo again for the talk. Thank you, Matteo.